So now we learned a bit about the basic communication principles, and we also learned that, well, there is not a single pair of users in a network, but there are many. So there are many communication flows going on. And so it's a quite natural question to ask, how is a network shared between different users or systems, communication streams? Okay, so let's have a look. We have to share links connecting the systems, and we also have to share intermediate nodes. Yes, we also share maybe end systems because we run many different applications like video, like audio, like email, etc. But this type of sharing, it's not what I mean here. This type of sharing, then it's more a question of the operating system sharing the resources, etc. So here we see that inside the network, we share the links. Here, this is where all the data flows over these links, typically fiber optics, and here are our terabits per second. So we share here, but we also share in the intermediate system. These are our backbone routers. They also operate on the terabit per second range. So this is where we share. And there are completely different ways on how we share these links. We'll have a look at this. Okay, so inside the network we share. This is something we have to handle with communication protocols. But also we share on the links to the end systems. So we run our communication protocols over these links, and we will send audio streams and video streams and our email and whatever over these links. So we share them. Okay, what are alternatives to sharing? Okay, I could think of, I know this is completely stupid, but maybe we have one link for video, or maybe another one for audio, maybe one for email, maybe one for this, maybe one for that. Okay, we know this from our everyday life, so we have different links for classical postcards and letters, and with another link for, let's say, talking to someone using the mobile phone, and maybe we have a desktop computer doing some other work, grid computing or whatever. So yes, there are situations where we do not share, but in general, sharing is the way to go, because this really looks completely stupid if we have here so many different wires for applications. No, that doesn't work. So we have one computer and we have one wire going out of the computer, and somehow we have to share this. And also in the big networks, there's one fiber and we share this fiber for thousands of different applications. Why do we do this? Well, it saves money. So sharing resources helps a lot. So, but there are certain requirements. So you cannot just say, okay, now share this. So we need some efficient mechanisms. Efficiency is always good. We need some mechanisms how to exchange the data. Okay, that's a basic requirement. So we have to be able to exchange this inside our distributed systems. So these are the different components connected by our networks. But besides that, we also need some efficient mechanisms to minimize what we call blocking due to multiplexing. So what happens? We share this wire, fine. Okay, then we need mechanisms. Now, let's say, okay, we have many basically sources here and different destinations. And so data flows over this wire. We share it. So there might be some data from A to B, and there might be some data from B to C, or whatever. Different both directions. We learned full duplex, half duplex, etc. The problem is, as we use this resource multiple times, we have to minimize blocking. The point is we multiplex different data streams on a single wire. What happens if we send two different data packets at the same time on the wire? We will learn that it's not only time, maybe same frequency, etc. So we need some mechanisms there. So it's not useful to send data on a wire that is currently already occupied by another ongoing communication. So we have to handle this. And there are different ways of how you can handle this resource sharing and how you can minimize blocking. Again, two basic principles. You see, in this lecture, it's all about very basic principle. So one way of doing it is reservation. You reserve something in advance. That's the typical way you do, for example, if you fly. So if you fly, you make a reservation and you have your guaranteed seat. So that's the same we can do for communication. So we reserve bandwidth in advance. The big advantage here is, okay, I know as soon as I have to do the communication or I have to fly, there's a guaranteed seat for me. Great. But you have to reserve in advance. There's another way to go, that's on demand. So I have to send something, okay, I just send it. That's, for example, the case where you when you use a car and you just go on the road with a car. Well, you cannot be sure that there is a space for your car. Maybe there's right now another car. So isn't reservation always the better scheme? Because then you can make sure that if you need the bandwidth, if you need your seat, it's available. Well, the problem is reservation always needs some overhead before you can actually transmit something, before you can use the resource. On demand, well, it's just, okay, let's try it. There's now the demand. Now I try to access. This could be much faster. And we will see that many communication protocols use exactly this scheme, on demand. On demand transmission of data, on demand usage of a resource. Reservation and on demand are both examples of what we call statistical multiplexing. So we multiplex traffic over a shared resource. So we can do this, let's say, for example, in a reservation scheme for a certain flow or train of packets. So first we reserve a part of the resource or the whole resource, and then we transmit a flow of data. We'll see that this is done in many situations when we know, okay, now we need resources for a longer time. Quite often, if we go on a packet level, we do on demand. That means with a single packet, we want to transmit this, and this then done on demand scheme. That means I've got a packet, and then I'm looking, for example, on the medium, and if the medium is available, I transmit it. We learn that depending on different layers, we will use this on-demand packet level transmission, but there are also situations where I use this reservation scheme. And many communication systems, they simply mix those schemes. For example, your cellular phone uses on a certain packet level this on-demand scheme trying to access the medium. And after being successful, you perform certain reservations, and then you can let the data flow over a reserved medium. But in the end, we statistically multiplex different communication stream over our shared resource. So let's give you some examples for this. We have a situation here with some end systems on the right-hand side, our destinations, and some data sources on the left-hand side. So those three sources now send their data via the same intermediate system over a shared link. And let's assume the overall capacity of this shared link is 30 megabit per second. And now we have a simple case. For example, each source needs 10 megabit per second. Okay? So 10 flowing down towards the intermediate node, going onto this shared medium. And there you see, okay, 3 times 10 megabit per second, everything is fine. What can we do? For example, we can make reservations that we send, okay, let's say this is from A, data from B, and from C. So we go A, B, C, A, B, C, etc. So we can make this kind of reservation for example, a certain time slot, and then we can multiplex the traffic, for example, in a fair way, that in the end, each of the node can really send 10 megabit per second, and it fits into this 30 megabit per second. Okay, that's quite simple. But what can we do, for example, another case where we have certain peak demands and certain flows of different durations. So now maybe a flow of some milliseconds with a certain peak demand comes with 10 megabit per second. A next flow from the next source, so let's assume source 1, 2, 3, has another demand, other flow duration, and it can peak up to 25 megabit per second. And yet another one 13 megabit per second. So what can we do? Can we say, okay, we first let, following the first come, first serve, the first flow through this shared link and block the next one? Or we could say, okay, you all can send at the same time, but we will learn how we can do this, limit each of the flows to 10 megabit per second. So we could say, okay, instead of first come, first serve, we say equal share of 10 megabits per second, and can say, okay, this is fair somehow. Or maybe we can also multiplex it in a way that, okay, maybe we have a peak in one of the flows where we do not have a peak in the other one. So somehow we can multiplex it in a way that they all send simultaneously and we statistically multiplex them. So do we do this, or can we do this with a reservation? What happens if we do not know the size of the peak? We do not know the duration. Do we do it just on demand? So if there's data, we try to transmit. What is the best solution? That's one of the very basic things you will learn during the whole lecture. Well, it depends. In this case, it depends on the application. There is no single best solution. Reservation or on demand, or everything is a kind of a synchronous fashion or a fixed pattern or whatever. It all depends on the application. For some applications, well, we can easily share it with this 3 times 10 megabit per second. For other applications, no, we need these peaks to go through, etc. We will learn what type of application needs what type of resource sharing. And one thing we can look at, for example, is such a flow of data has certain peak rates and has certain average rates. So remember, so we have, let's say, the rate on the y-axis and then over time here on the x-axis, and then whatever, there might be some peaks in the data flow. So this is my peak rate. And then we will have something, okay, somewhere here, maybe we have the average. So if I want to make sure that the traffic flow goes through our link exactly the way I've shown it here, then we have to make reservations here for the peak. So if we do not do so, the peak will not go through. So reservation must reserve the peak. But how do we use really the link? Well, that's the ratio of our average compared to peak rate. So let's see. The problem is, we reserve for the peak rate. But if the average is low, then we underutilize the whole link. Yeah? So we cannot build roads for the rush hours so that all the rush hours really go through and there's no traffic jam, because then we need something like 100 lanes. So when can we really use reservations? Well, it depends on the ratio of the peak to the average. So, for example, a classical so-called constant bitrate data stream. There once was a telephony system called ISDN that had 64 kilobit per second constant bitrate, 64. So one of the first digital fixed telephone systems. So 64 kilobit per second constant bitrate. Then this ratio is 1, and reservation works pretty well, because then peak is the average, and that's fine. So still, today we have different codecs, and thus we use variable bitrate. But for voice, still the ratio is something like 3, for example. Then we can do reservations, and we can mix different voice streams over a wire. So if we say, okay, there might be the peaks, but it's fine. We can reserve for certain kilobit per second. But what happens if there are applications that create very bursty traffic? Bursty, that is when we have a communication and a sudden burst of data. When does it happen? For example, browsing the web. There's some communication going on, so websites checking where your mouse pointer is and reloading stuff, etc. And then you click on a link, creating this peak. And then we have ratios that are way more than 100 or maybe 1,000. So you download suddenly a lot. This can be quite bursty. How do we perform reservations here? That's quite complicated. Especially if you think at classical telephone networks, they were made for voice communications. And this way you can use reservations there, not the original internet. On the next slide I will show you what the consequences are. But for telephone networks, that was the classical thing to do. Okay, you know that something like maximum, let's say 2% of the customers will use the telephone network at the same time. And this will tell you something about the dimensions of your links, of all your intermediate systems. And you know, number of customers, and typical connections. So this can be calculated. For the internet, we have this bursty traffic. Now I send an email. Now I download something. How should you reserve something? So that was a complete different way of thinking. And this also influenced the way of implementing this sharing of links. And the two ways of implementing sharing links is circuit switching, that typically comes together with a reservation, and packet switching, that typically comes with on-demand. What does it mean? For circuit switching, first you set up the circuit. So for telephone, classical telephone system, first you dial the number, and this tells the system which wires to connect. So in former times, this was really wires connected. And after setting up this connection, you can actually use it. And for telephone, it was quite clear. So 40% of the time A talks to B, 40% of the time B talks to A, and 20% is silence. Well, rough numbers, for example. And after you finish, you have your phone. So you basically clear the resources. So you shut down everything. So that's it. That's the end. So shut down or cut the connection, clear, whatever. So the typical phases of circuit switching: reservation. After the setup is that if the setup was successful, you're sure you can use the resource. So if you dial the number and someone picks up the phone on the other side, you can be sure you can use the resource for 10 seconds, for 1 hour, 10 hours, 100 hours. Because you have switched this circuit, you can use it until you hang up the phone. So that's, for example, one of the reservation schemes. We will learn many more schemes during the lecture. On the other side, we have this on-demand usage. And this often comes together with this packet switching. And packet switching, that means simply, well, send whatever you like to send. That's like your postcard or your letter. You just take the envelope, put it into the box, and that's it. Now I have the demand to send something. Now I send. There's no reservation. Nothing needed. And that's the basic scheme of the heart of the internet. We will learn also reservation protocols in the internet, but that's the heart of sharing resources. So two basically different ways of how you can do this. So to repeat, circuit switching, you establish during the setup phase, you start establishing a communication channel first. That's the first step to establish the communications channel. So that's step number 1, this setup, or whatever you call it. And then step number 2, data may flow, unidirectional, bidirectional, so telephones typically bidirectional, full duplex, half duplex systems, whatever. So you set up the channel, and then 3, you tear down this connection. And inside these elements, it means that during the setup phase, you really, and that was the idea of those switches, you really create a communication channel. In former times, this was really a copper wire, and then you really had a mechanical switch connecting the wires. And even before that, you had someone sitting there at the switchboard, then connecting really different customers. And later on, the switches, full electronically, basically, they simulate this connection, this connected copper wire, by assigning certain time slots. That you start, incoming traffic comes in certain time slots, and then you create outgoing traffic at certain time slots with guaranteed delays. So for example, the switch has a delay of this and that nanoseconds. Guaranteed delayed, and as soon as you have set up the connection, you can guarantee also the data rate. That's one of the big advantages. So you know exactly after setup, you know the performance parameters. So that's one of the biggest advantage, predictable performance. And this is why many like this circuit switching for applications that have to guarantee something, guaranteed access time, guaranteed reaction times. So this is the switching itself is very simple. As soon as you have set up the path, remember that was this device. So you come in and then you decide, okay, I go out here. As soon as this is set up, it's very simple because then you know exactly, okay, what comes in here at this input 1 goes out at the output 17, for example. So once the circuit is established, this is very simple. And when do we need addresses? Remember the telephone. Addresses only in step 1. During the setup phase, you need a address, the telephone number, for example. After that, while talking during this transfer, we do not need any address anymore. So you don't have to dial the number for each and every word. No, because the connection is set up. So we need the address only in the very beginning, not while transferring our data. That's good. Disadvantage. What do we do if traffic is very bursty? Or only very short flow of traffic? Because then we always need this step of setting up. This takes time. So it's much easier just to drop your letter. That's it. Just to send some data. Or remember, if I have bursty traffic, then I have to make a reservation for this peak rate. Otherwise, traffic will not go through. So that's very inefficient. The setup and the tear down can be quite complex. It takes some time. So you have to find your way, and this adds delay to the transfer. So you cannot just drop your data. No, first setup, then transmit. And how to adapt to failures, it works. We will learn some of the technologies, what you can do there, multi-protocol label switching and switching over to other paths, etc. But it's not that simple, because once you've set up your path in this first phase, you use this, and if then something happens, you have to re-establish a path and you have to redirect the data. Typically then the whole connection breaks. So it's not that easy. So what is the alternative? Well, packet switching, this on-demand character. That means there's only one step. Just send whatever you have. Okay, how does it work? Well, we have our sources. We have our sources with packets. There we have the gray packets and the yellow packets, or maybe some red packets, whatever. We send them, and here these devices have to decide for each and every packet where to forward it. Maybe there are some other outgoing connections. So as you decide, it goes this way. Plus, you have to time multiplex. So we don't want to create overlapping packets, something like this. Not a good idea. So we have to multiplex this, first the gray, then the yellow, then the red one, for example. And then again here, we have to check the packets. Do they go this direction or do they go that direction? So that means that in contrast to circuit switching, now each and every packet needs at least a destination address. So for circuit switching, only during the setup phase. For packet switching, we need the address in each and every packet. That's exactly what you do with your postcards and letters, the classical ones you really write. You have to write the destination address on each and every postcard. You cannot just dump a whole bunch of postcards into the box and say, okay, I wrote the address on the first one and all the others should simply follow. No. So we always need some space for address in all these packets. And if you send millions of packets to the same destination, all the packets need an address. And that's the classical scheme you have in the internet for what we know as layer 3, our networking layer where the internet protocol is. So, advantage, much more flexible. So we can way better multiplex, way better adjust to bursty traffic. Imagine we have many packets, many of the gray packets, for example. If it fits, it fits, and then from time to time a yellow one, whatever. So way more flexible when it comes to use of the network resources. If a new packet fits in, great, we just do it. This is on demand. Okay? So, and if we have trouble on one of the paths, we simply take a packet and reroute it because there's the address. Each and every packet has an address. So we can take it out and reroute it. No problem. So that's great. A problem, well, remember, if you have this intermediate system, typically called a router, if traffic comes in and we do not have any reservation, we have an outgoing link, it might be the case that we need a buffer, a queue, because we cannot send the packets as fast as they come in, for example. And now, depending on the status of this queue, the performance may become unpredictable. Because if there's a lot of traffic, it takes longer. It's like with the car. If there's rush hour, it takes longer for the same distance over the highway compared to if you go after midnight. So it's unpredictable. Plus, we have an overhead because remember, all the packets have to carry an address. So, unpredictable, we need some buffering, we have some overhead, but much more flexible. And the flexibility is one of the reasons why the internet loves packets. So, for the internet, the traffic, all the traffic uses this packet-oriented model of sharing using the internet protocol. So, some more questions. Why do we need this sharing of resources? We have very basic questions. So why can't we just have the resources? I want my resources for myself. Think of cars and roads, etc. And how can we achieve this sharing? What different schemes? So what are the pros and the cons of reservation versus on-demand? And now think of applications. Which kind of application may like this more reservation schemes and the more on-demand schemes? Then I just explained circuit switching and packet switching. They've all their advantages and disadvantages. And the advantages and their characteristics also give you a good idea why, for example, historically, telephony system was a circuit switched system. But why is it today also packet switched in many, many cases? So we use voice over IP, over whatever, LTE, over all these systems. So this is all packet switched. So why? And maybe also find out what is needed so that we can do telephony over packet switched systems today.